This is the second video in my short series on the mathematics of epidemics and pandemics. In this video, I'm going to look at the spread of disease in the initial stages of a pandemic. I'm going to use some of the calculations that we did in the previous video, so if you haven't seen that, then I'll go back and watch it before continuing with this one. So, let's calculate the spread of a pandemic. We've got three different groups of people, as we discussed in the last video. We've got the uninfected that are susceptible to being infected. We've got the infected and infectious people. And then we've got our removed populations, so people that are no longer able to give or get the disease. I've put a few assumptions that we made in the last video down the right hand side here. So we're assuming a population of 401 people. The average person interacts with 10% of the uninfected population in a week, and the chance that the infected person infects someone in a given interaction is 5%. We're also going to assume that the infected people are infectious for 2 weeks. So, in week 1 of the pandemic, we know that one person has got the disease. That's our red person in the middle there, which means that the rest of the population could get the disease, hasn't got it yet, and certainly hasn't recovered from it. So we've got 400 uninfected susceptible people and one infected person. Let's jump to the start of week 2. So, as we calculated in our last video, the infected person has infected 2 people on average. So at the start of the second week, there's 3 infected people. We've got our one original case, who's still infectious, because we said that the infected remain infectious for 2 weeks, and we've got our 2 new cases. Because the disease has been going for less than 2 weeks, nobody's yet been removed from the disease. On to week 3. Just a point to note about this model, a simplification. We've assumed that anyone that's been infected within a week is infectious from the start of the very next week. There is always a delay between being infected with something and being able to pass it on, but typically people will be infected at different times throughout the week and therefore will infect people from different times throughout the next week. But it's much simpler to assume everyone can start infecting from the start of the next week. So, in week 3, each of our 3 infected people has infected about 2 people each, on average. So we would have 9 infected people during that period, but one of them has now gone. They were infectious for 2 weeks and they've been removed. So, at the start of week 3, we've got 8 infected people and 1 person that's been removed. They're no longer infectious. Here are the figures going forward all the way out to week 6. I've got an Excel model that I built that spits these numbers out for me, so I wasn't just calculating them all by hand. That would be a bit much. I'd say it's quite hard to engage with just numbers on a page, so let me put a graph up to help us see what's actually going on here. This is what the start of our pandemic looks like. The orange is all of our uninfected people, the red is our infected people, and the green is the people that have been removed from the population. They're no longer infectious or able to be infected. How do you read this graph? You can look at any particular point in time that you're interested in, so here maybe week 2, and look down at how much red is there. Here, there's not very much red at all. We know that the number of infected people there are is actually 3, and then everyone else, all of the orange, is uninfected people. Let's look at a different point in time, say week 5. Now we've got some people that have had the disease and recovered from it. They've been removed from the population. We've got quite a few infected people, but we've still got a decent chunk of the population that aren't yet infected with the disease. So whilst this is a super interesting model, how useful actually is it? Well, it's quite useful for understanding the spread of infections at the start of a pandemic, despite being very, very simple. However, it becomes much less useful when a larger percentage of the population have the infection, because it doesn't take into account that the infected people may all be infecting the same uninfected people. So if Alice and Ben both have the disease now, and they're going out infecting people, and we think that each one of them has infected 2 people, but maybe both of them have infected Catherine, the likelihood that we're double counting infections becomes more and more likely as a pandemic progresses and more people have the disease. In the next video, we're going to look at a slight twist to the model that takes this into account. For now, however, let's think about what this model can actually be useful for. So it can be very useful for comparing the initial spread of pandemics under different assumptions, because it's very, very easy to change the inputs into this model because it's such a simple model. So we can compare the impact of different interaction levels within a population. Maybe people within a particular population are more likely to come into contact with each other. Maybe there's different levels of disease infectiousness, which is useful for comparing across different diseases. And same with different lengths of time that the infected are infectious for. It depends a lot on the disease in question. So let's have a look. How does the spread of pandemics change if our assumption about the percentage of the population that each person interacts with changes? In the model we've been using so far, we assumed that each member of the population interacted with 10% of the population during any given week. I've reduced that by 2%, and you can see very clearly in the graph the difference that's made. The infection has spread far, far slower, which can be hugely useful for the government in giving them a huge amount more time to prepare, whether that be ordering in supplies for hospitals, more time to develop a vaccination. The next thing that I looked at was the impact of changing the infectiousness of a disease, and the impact is crazy if you look at those graphs. So in our previous model, we've always assumed that it was 5% infectiousness. So if an infected person interacts with an uninfected person, there's a 5% likelihood of the infection being transferred. I've increased that to 7%, and you can see the difference it's made. It's huge. The third thing I've changed is the length of the infection. So in our previous example, we've assumed 2 weeks. So once you've got the disease, you keep infecting people for 2 weeks, whereas now if we only assume it's 1 week, again, quite a big difference, the disease spreads much, much more slowly. This is useful for explaining the differences in shapes of different diseases as they evolve over time. As I keep saying, it's a very simple model. There's so many ways in which we can improve the model to help us better understand the spread of pandemics and so formulate better policy responses. Here's a few examples of things you could do. You could assume some prior immunity, or maybe we introduce a vaccine halfway through. We could assume that different groups of people in the population have different susceptibility to the infection. Maybe they're more or less infective. Maybe there's different interaction levels. Maybe people change their behaviour because they realise there's an infection and they go crazy and buy loads of Lurol, or maybe get vaccinated or wash their hands more or interact less. And we could assume maybe there's some clustering in the population. So maybe there's likely to be sort of some groups interact more with each other and we see sort of spikes in the infection in those groups. That's the end of part 2. In the next video, part 3, we're going to look at how a pandemic changes over time, so beyond the initial stages. How do different factors impact how many people end up with the disease and when they end up having it?